The night sky looks peaceful and unchanging, but that stillness is an illusion. The space between the stars is a volatile ecosystem, churning through a cycle of birth, life, and catastrophic death. This cycle begins in a stellar nursery, a cold, dark molecular cloud made of hydrogen gas and interstellar dust. Over many thousands of years, gravity pulls this dispersed matter together, gradually forming a single, increasingly dense knot. What looks like an empty void is actually a dense concentration of matter, containing the precise ingredients for the most energetic events in the universe. A disturbance, like a shockwave from a nearby supernova, triggers a final collapse. The cloud fragments, and the material begins to spin into a rapidly accelerating disk. Gravity crushes the center of this disk, driving temperatures up. At the core, the heat climbs to a mind-boggling 15 million degrees Celsius. At this threshold, hydrogen atoms are forced together so violently that they fuse into helium. This process, nuclear fusion, releases the massive amounts of energy that define a star. This birth is announced by violent jets of gas that erupt from the center, accelerating material across light years of space. The star is now born, but its ultimate lifespan and the manner of its death were determined by the exact amount of mass it gathered from the cloud. The star now enters the main sequence, its longest phase of life. This stage is a perpetual, violent tug-of-war between two opposing forces. Gravity acts as the aggressor, relentlessly trying to crush the star's mass inward. Fighting back is the outward thermal pressure generated by nuclear fusion in the core, which holds the star in a state of equilibrium. This balance is entirely dependent on the star's finite supply of hydrogen fuel. The stability we see is a temporary state. The star is burning through its reserves to delay an inevitable collapse. A star's strategy for surviving this tug-of-war depends on its initial mass. Low-mass stars, like our Sun, are the marathon runners of the cosmos. Their weaker gravity allows them to sip hydrogen fuel slowly, potentially shining for trillions of years. This chart compares consumption rates. A massive star's crushing lead requires it to burn fuel at a furious pace to hold itself up. They exhaust this fuel in just a few million years, a cosmic blink compared to smaller neighbors. Having more mass does not buy a star more time. It simply ensures a faster, more violent demise. When the hydrogen finally runs out, the outward pressure stops, and gravity begins the final crush. A low-mass star expands into a red giant before gently shedding its outer layers into the void. This creates a planetary nebula, leaving behind a glowing, Earth-sized core known as a white dwarf. These stars die quietly, leaving behind a bubble of gas and a dense core that will slowly cool in the dark for eternity. Massive stars face a more desperate end, fusing heavier elements like carbon and neon until they reach iron. Iron is a mechanical dead end. It absorbs energy instead of releasing it. This instantly eliminates the outward pressure, causing the core to collapse and rebound in a matter of seconds. This rebound is a supernova, the largest explosion in the universe. It leaves behind either a neutron star or a black hole. These massive stars leave behind the most extreme objects in nature, remnants so dense they can trap light itself. While the cores remain, the gas and heavy elements cast off by both planetary nebulae and supernovae drift back into the cosmos. This enriched material drifts until it eventually seeds new molecular clouds with the heavy elements forged inside the dead stars. Often, the shock wave from a dying star provides the exact disturbance needed to trigger the gravity of the next generation. The universe is a giant recycling engine, where the cataclysmic death of one star acts as the trigger and raw material to birth the next.